Yeah. So, okay. Is my screen visible to everyone?
Yeah, it is.
Cool. So today we're going to be covering basic linear regression and what does it mean? Why do we do basic linear regression? How do we do it? We're going to answer all these questions today, and we are
Yeah,
covering
classes
only the
going on?
basics. So for more advanced level tutorials, please stay tuned or look for resources in our data sheet as well, in a resource sheet as well. So firstly, why do we even do regression, right? So a direct, simple answer to this is cause-effect relationship. To understand the cause-effect relationship between our variables, right? So in psychology and in allied sciences and other fields, we often are faced with research questions that require us to establish some form of a relationship between two variables, right? And the most common form of variables that we know are two. So one is dependent variable and then another is independent variable, right? So the dependent variable is the one which is measured. I mean, both of these are measured, of course, but the dependent variables are the ones on which the effect of our experimental manipulation is studied, right? And these are often known as outcome variables when we talk about regression in this context. And then the second class of variables are known as independent variables or explanatory variables when it comes to the context of regression. And sometimes we also call them predictors. So these are the variables whose effect we try to study on the dependent variables, right? So one example of this is let's say a researcher wants to study the effect of stress and eating patterns on mood scores, right? So in this example, your stress score and your eating pattern scores would be your IV, that is independent variable, the effect of which you will study on the mood scores, right? And these are also known as explanatory variables or predictor variables. And your dependent variable or outcome variable would be mood scores, right? So this will be your dependent variable, right? Now, another way in which we study, another reason why we do regression is to understand the predictive effect of variables, as would be clear. Let's say, in some research question, we are facing with one or maybe two predictor variables, like in this example, right? So here we were trying to understand the effect of stress and eating patterns on mood scores. So essentially, we have two IVs here, right, and then one DV. So by doing regression, we are essentially trying to understand the predictive effect of each variable and also combined effect of all the variables together in the form of interaction on the dependent variable, right? So finally, just to bring it all together, we do linear regression to in order to understand the linear relationship between two variables, right? Or between two sets of variables, that is dependent variable and independent variable. Now, any question before we dive into the data sets and examples of how we do it in R? Any questions, anyone, in the basics? I hope it's clear. If there are any questions, please feel free to ask or write in the chat section. Okay, cool. So, since there aren't any, let's just continue. Sure. So now, just going over another basic point, this is how we represent a linear regression equation. I mean, mathematically. So y equals to beta naught plus beta into x plus e. I know it sounds a bit non-intuitive to understand and a bit mathematical, but it's going to be all very easy. Don't worry about that. So in this equation, y essentially represents the outcome variable, right? So y would mean the value of a dependent variable, right? And x represents your independent variable. One error that I made here is I did not put a hash because for any comment that you put, you need to start it with a hash key, this one. So in this equation, again, to reiterate, y represents the outcome variable and the dependent variable, and x represents independent variable. And you must be wondering, what is beta naught and beta, right? So these are called, betas are basically called coefficients, right? So what do they represent, right? So let's say the beta naught means that the value of outcome variable, that is dependent variable, when x is 0. So all of this term is 0, and that's the value of y, right? And beta represents the coefficient or estimate of x, right? So it's all going to be very clear. I'm just going to explain this equation and the related tests with two examples today. So don't worry if you don't understand all of it right now. We are going to use examples to understand this equation. Okay? Any questions till now? If you have any, please feel free to write it in the comments or chat box. We're going to review it at different checkpoints. Okay? So moving further, I've just recreated or simulated a fake data set. So this data set is all about the social media usage hours, essentially how many number of hours people spend on an everyday basis on social media, right? And another variable in this data set includes their academic scores, right? So essentially, we are trying to understand how social media usage uh, leads to or affects academic scores of individuals, right? So this is the research question that we are interested in studying in this data set. And I'll also show how this data set looks like. So we have around 5,000 entries, as you can see here. And so which means there are some 5,000 participants in our study. And the social media usage scores are given here. These range from 0 hours a day to 16 hours. That's the maximum. And the academic scores range from 20 to 100 for each participant, right? So here we are trying to study how number of hours spent on social media every day or on a daily basis affect the academic score of participants, right? And just ignore this column. I'll come back to it later. Okay, so this is pretty simple. And first, what we can do is we can just try to describe our data, right? So how does the data look like? So regardless of whatever data set, however complex, however simple it is, we should always start with going over the descriptive stats of your data. So that would include your mean, your median, your skewness, your CI and stuff like that. So I'm just going to use a very simple function as part of the psych package in R to describe our data set. Right. So R tells me that it could not find the function describe because we did not load the package, right? So I'm just gonna load the package. It's contained in psych, right? So I've loaded the package and now it's gonna show me some quick descriptive stats for my data, right? So it tells me that there are four variables: ID, social media usage hours, academic score, and academic index. And there is an asterisk next to ID because R wants to tell you that it has only characters and no numbers, right? So as you can see, our ID only has P1, P2, P3. So these are just characters. These are not taken as numbers, right? So, and then it also gives you how many number of total data points we have in each variable. And it also gives you a mean. So the average number of hours that people have spent on a everyday basis in our data set is 8.52 hours, and the average academic score obtained by them is 53.48 out of 100, right? It also gives you standard deviation, median, then trimmed median and minimum and maximum as well. So minimum number of hours that people have spent on social media is 1, and the maximum amount of hours that people have spent on social media is 16, right? And again, the same thing for academic scores. The minimum number that someone has received is 20.96, and the maximum that someone has received is 86.31 out of 100, right? And this gives you a range as well, and skewness and kurtosis and standard error, right? So what it does is essentially is it helps you understand the head or tail of your data. It helps you get familiarized with your data well, and it helps you get started, you know. Now, after just describing, we can go for visualizing, right? So, after looking at some of the basic descriptive stats, it's always nice to see visually how your data looks like, right? So, the most simple way to do is make histograms. In R, how you do it is you have this function called hist, and the best thing about R is whenever, if you don't remember the entire function, you can just start typing. And most of it is quite intuitive. So if I want to make a histogram, the command starts with HIST, right? As I'm writing HIST, it's gonna give me all these hints, or it's gonna use my input as a way to assess all these possible functions in its list, right? So I need to use this function. So I will select it, and then I'll mention my data set, which is our data one, and then I'll mention my variable, right? So I use dollar to specify my variable, right? And then I can just write SMU hours, right? So this is done to understand the distribution of the social media usage hours in my study. Yeah, as you can see, this is a distribution. So as you can see, most of the individuals, most of the participants in my study have their social media usage hours between 0 to 5, right? As you can see, this peak at the very beginning, and uh, and a lot of them have it quite constant between 10 to 15 hours, and then 5 to 10 hours, right? And then if I want to visually see academic scores as well, I can do that here too. See? So as you can see in the middle, a lot of them have scored in the middle, ranging from 30 to 70 or 80. And there are only very few people who have scored low, and or very few people who have scored really high, right? Now, the best thing for me would be to now plot, right? So, again, going back to my research question, right? I wanted to understand how social media usage affects or influences or is linked to academic scores of participants. So, what I can do is I can just make a plot, like a scatter plot out of it, right? So, for that, I will use this command plot plot, and I'll mention my independent variable in the x argument, and I'll mention my dependent variable in the y argument, right? How we do it in R is quite simple. We first mention our data set, and then we use a dollar to specify that we want to use a particular variable of the data set, right? So here we have mentioned social media usage hours as x and academic scores as y, right? So if I'm just gonna quickly run this thing. Okay, so it gives me this, strong linear relationship when it comes to the scatter plot, and I can explore more by including a linear regression line, right? How I do this in R is just add another command which says abline. So your abline is used to add the linear regression line to your plot. So right now I know roughly that it's kind of related to each other because I can see a pattern in the data. As you can see, as the social media usage hours increase, the academic scores decrease, and it happens in a very consistent manner. I can just add this line too, right? So when I do this, it shows me a very clear line, and this line represents the goodness of fit, right? This concept of goodness of fit, right? So it tells you that in this equation, we have regressed academic scores against social media usage hours. By this statement, we essentially mean that we want to understand how academic scores are dependent on social media usage of participants, right? And this line represents the goodness of fit, right? This line represents the best possible line that can go through the data and represent a linear relationship between the two variables, right? Are there any questions till now? If it's clear, can I just get a yes in the chat box so that I know that everyone is getting all the points? Okay, great, great, great. Thank you so much, guys. Okay, let's move on. Great. Let's move on. So this line is called goodness of fit line. Now moving over, you must be asking now, what do we do? How do we proceed after we have visualized it, right? So now what we can do is we can go for the basic test and assumption, right? So whenever we do any kind of statistical test, such as linear regression, logistical regression, or um, correlation or analysis of variance, or whenever we compare means in t-test and ANOVA, right? We always have some basic assumptions, right? And for linear regression too, we do have some basic assumptions, and these should be met or have to be met in certain cases. Now, the first assumption or the first thing that we need to look for is the nature of our variables. Now, please focus because this is very important to understand right now, right? So, for linear regression, your variable, the outcome variable, which is your y in this equation, or which is your dependent variable, right? It should be continuous in nature, right? By being continuous in nature, I mean that it should range over a particular, um, starting point and over an end point, and it should be continuous in nature in a way that there should not be any discrete or categorical values in our variable. So an example of this would be height, right? So height ranges from, let's say, 135 centimeters or 130 centimeter, and this is just my rough estimation. A lot of folks might be shorter than that or taller than that. So it ranges from, let's say, um, 130 centimeter to you know um, 190 centimeters, right? And some people might be 150, 160, 150.5, 155.5, right? So it takes on these continuous values, and that's why height is a continuous variable, right? Now, one variable which is not continuous in nature or can be called as categorical is gender, right? So, some folks identify as females, some folks identify as males, some folks identify as transgenders, right? And other categorizations, right? So this is essentially categorical in nature, right? So there are different categories on in which we can divide each participant's data point. So that's why these are called categorical in nature. Now coming back to regression once again. For regression, it is important that your outcome for linear regression, essentially, it is important that your outcome variable should be continuous, right? Your outcome variable should range over a particular set of values, right? Now you must be asking, what do we do if our outcome variable, which is our dependent variable, or y in our equation, is categorical, right? What do we do? So essentially, that is covered in under the domain of logistic regression, right? When we have categorical when we have our data point, when we have our dependent variable as essentially categorical in nature, which takes on different categories or outcomes, then we go for logistic regression, which will be covered later on, since it has a lot of advanced stuff in it. So now we're going to look at, now we're going to come back to our linear regression session, right? So most of the theory is now done. I want to ask once again, do you have any questions? Before we
Yeah,
jump.
I had a doubt.
Yes.
Yeah, so basically, I wanted to know if I'm getting it right or wrong. Just let me know.
Sure.
So when you said that when we say that a data should be continuous or like a variable should be continuous in nature, be kind of limited to a particular range. So are we saying that there shouldn't be outlier
Both the
schools?
parents' side don't want him. Either mother's side they don't want him,
Yeah, that's a great question.
advantage
So,
of the grandparents, yes, forced
no,
all
that's
the
not what I mean.
copy
Of course,
documents,
there
sold
can
it
be
off.
outliers. Outliers are
When money
essentially
was there, all
extreme
his
values,
friends were
or
united with him.
Yeah, I
not
know.
normal
And
values that you
after
would get in
enjoying
your
his
data
money in
set.
Goa, spending 5 lakh,
So,
10 lakh, 20 lakh,
it depends.
this guy did
So,
not
we
realize
deal
the
with a
worth
lot of
of
data when
money
it comes to real life
fully.
questions,
Now,
right?
today, no friend
We deal
wants
with
to
data that
accommodate him.
can range from
Uh,
100 data points
we
to
throw him off at
30,
times. We
40,
tell him to
or
quit the
even
job.
to
We don't decide
5,000 or
associate.
10,000, right?
Again, he'll come
So,
back
I
crying.
think when it comes
We
to real
also
life
feel
data
bad.
sets,
It's not his mistake. It has
Yeah.
happened.
outliers are
Even here we
always
had a
there.
lot of this
I mean,
tenants from
thinking of your
Kerala who
data
used to
set
use
without
him
any
almost
outliers
for
is a
beggars.
dream for
He was
anyone,
in
to be
night
honest.
shift.
Like,
Yeah.
Just
it
with the
doesn't happen
giving
like
some
that.
weed or
When I
others
say
and
that
tell, okay, you do this.
our
And then we
variable is
shifted him to
continuous,
day shift.
I mean that it is
Then
assumed or it is
they,
expected that it would
this
take,
guy went
on a
into too
certain
much of
range, right?
psycho mode.
But sometimes
Then we
it
had to
may
ask him.
actually
We
go
tried
for
correcting
extreme
him.
values based on
He
how
told
we have
this is
collected the
something like
data,
class
or
18.
depending on a sample.
You
What I mean
can't do
is, it does
anything. He
not
needs
have
full
proper
thorough
discrete
treatment.
He
categories,
needs a real
and it cannot
Otherwise,
be
and we
put in
asked
proper
Ram sir how
discrete
much may
categories,
cost in your hands.
in my
He
data set.
told
So, for
for
example,
sitting, you will be
let's
paying
take the
around 1
concept,
lakh
let's
plus.
take the idea,
I
let's
was
take
thinking
the
1 lakh.
concept of height, right?
Like you
So,
go, you get
let's
him
say in
treated.
my
First, we
data
have to
set, I have
diagnose him,
measured height
everything.
of 10 people.
Then, if you get
That
a
ranges,
person where
from
he can
140
really
to
troubleshoot his
165,
stuff, it will be
uh,
very expensive. Per
let's
sitting,
say 5,
one, two,
right?
three sittings, it will be 1 lakh.
186, 124,
It's
After,
very
134,
tricky
and
actually.
150, right? So
Very
these are the
tricky.
6 height
It's
measurements that I've
he
taken,
has
right?
he has like
Now, of course, when I
substitution.
plot this data,
He has
of
like
course,
big trucks,
one of
or
these
whatever
values or
it
no,
two
he
of
is.
has
these values
consumed
will
to highest of
look
highest
like
level.
a
Because
outlier in
now
the
his
in our
tolerance is too
plot.
high also.
But
Small
So
small
this
if,
is
if
not
he drinks only, he's
representing a
stable.
categorical,
If he does not drink, he'll be shaking
categorical
like this.
That's bad. Yeah.
range. This is
So
representing a continuous
even
range
this
where it
guy
ranges from,
was
let's say,
into that
140
state. They
to,
put him in
it
rehab.
ranges from
He
1
got
120, and
25.
it even goes to
This
176.
guy
When I try
is
to
kind
summarize
of
my
not
data,
ready to
I
change.
cannot say
The same thing is
properly
first he has to
that
drop his substitution.
5 people or 3
Second, he
people out
has
of
that has
6
to be
We
corrected.
give him
have
biryani to
heights
eat
as
lunch, and
120, or 4 people
funniest
out
thing
of,
is we
let's say,
eat from
6
all these
have
local
heights
stores.
as 180.
For him
I
only
cannot
KFC,
describe my data or
Empire
variable
Hotel,
in terms of
Yeah.
and
proper
that food
categories
also
in
he
this
wastes, he
case.
won't eat.
And
If it's
if I
happening
contrast
around
this
30,
example
40,000
versus
here,
a
his
case
expenses are
where I
1
would
lakh.
have made categories in my height
So
variable too,
we tell
where I
him,
would have
see
said
that
that
he is involved with a
somebody,
lot of bettings,
if
lost
the first
money there.
person has a
He
height
got cheated
from
with
ranging
everyone, sir.
between
He's with us
120
from
to
7 years.
140,
Even I
the
told him, you
second
go to
person
an
has a
IT
height
company, they'll
ranging
put you
between
on
140
R&D,
to
research and development,
160.
you've gone
Third
cave.
person again has a height
Uh,
ranging
at
between
times, when he
120 to
gets too much
140,
angry with us, we
right?
go to bar,
And
he'll drink
fourth
nicely, he'll
person
call us.
has height
Randomly he'll
ranging
call
from
us, well, be
140 to
ready, I'm ready
160.
to kill you
So
guys,
here,
I'm
as you
coming
can
with
see, I have
knife.
essentially
We have
created
like
these
Vietnam, we are
categories,
waiting
right?
for
Where
you.
I can
We
say
don't distract
that
him
in my
basically.
data, there are
He
two
gets
people
upset by
who belong to
himself.
the category
At
of
times he's
120 to
really nice.
140 height range,
At times
and
he's out of
there are
luck.
two people who belong to this category of 140 to
Now we have put
160
him
height
back to
range, right?
housekeeping.
So again, the nature of these
Not this
variables, how you
society,
have
other
measured, how your
society.
data
He
looks
has to
like,
go there,
it
do
highly
his
depends
housekeeping.
on
But
how
he
you
clearly
have
updated
structured
his
your
grandmother.
research design,
Every day he
how
brings 2 to 3
you have
pack of this
formulated your research
without his
questions, and
knowledge.
how you are going to measure them.
We
Is
updated
that clear?
to their grandmother,
Yeah,
saying
thank you.
that
That was very well
they're
explained.
also not ready
Okay,
to
thank you so
accommodate
much.
him, sir. He
Okay,
drinks every day
let's move
Old
on.
Monk.
So now,
If he drinks
the
this only,
second
he's stable.
thing
If not,
that we
he's
need
not
to look
stable.
for is normality. Of course, the good old normality test that we,
No, anything he
all
said,
do
even he
before
gets
all the
1,000
tests
rupees, it's
whenever
hopefully
we
on
do any kind
benefit.
of
He's
statistical
not eating
significance
good
test.
food also.
So now in R, the simplest way of doing this is Shapiro test. So
Once
it's
he was
pretty
caught by
simple.
CCB
You
also.
just have to
In
write
Tadepalli, we went, we
Shapiro,
recovered him from
and
there
then
at
R,
4 of night. And
R
then we
gives
told
you
stop,
that
cut off all your friends. Don't
R
allow them
gives
to
you this
come
hint
here.
that
Or
this
you
is the
don't
test
go
that
to
you're
their
looking for,
place.
maybe.
Otherwise
And
you'll
then
spoil
I'll
our
just
district. And all
mention
the
my data
students also
set, which is R
influence him.
data 1, and then
You
I'll
get us this, get
show
us
R
that,
that
I'll
I
give you
want to
1
now
lakh,
go
2
for a
lakh.
particular
We tell him,
variable
you all
under
are
this data set,
constantly able to work.
which is
Let's see
SMU
why
hours,
you are
right?
not stable.
And if I want to
Sam
see
is able
this,
to perform what is
so R
as
gives
an
me
Indian, what we are
this
able
p
to
value, which is
thoroughly
less,
accept so
much less than 0.001, which is
They were
significant,
all on seventh floor.
which
It was all
essentially
getting
tells me that
renovated.
the distribution
So
of
we
this
posted them
variable
to the
is
first
significantly
floor.
different from that
Otherwise,
of normal
nice
distribution,
people.
right?
We removed
And
Joshua
which
because of his
roughly and
hypertext.
more simply tells
We
us
used to
that
see him
our
talk, shout,
variable may not be
loudly talk.
normally distributed.
Then we
And
told
another way to
him.
visualize this is using QQ plots,
He
right?
went to Banagata branch.
I'll just show you how to do that.
Only
Long and then
Okay.
our
I
data
studied
one.
in that Christ.
Oh,
let's say
Bangalore
numbers.
road crash.
If I go for this one,
No, now what I am
and
seeing
then
is
if I would like to
where
draw
before
a
students are
line through
more
this,
accessible to all this drugging, smoking, but they're
keep
not
this,
realizing they're spoiling their life.
yeah.
What we have seen here, what was told with all this,
So
they put
as you
their
can see,
parents
there is
into
some kind of
lot of
a
stress,
linear
lot
relationship
of
between central content and critical
hatred
content.
mode.
Also,
And
don't worry,
they also are not
don't get
happy.
confused here.
Student is also
We'll
not happy.
take this issue
Let
later,
them
or
enjoy, but
take
not to
this
an
topic in
extent where
much
you
more
kill
detail about
yourself, kill
normality.
your family,
But right now, you
destroy
just need to
your
know
own life.
that QQ plots
Your
is
family is
another
having
way
a lot
that you
of
can
dreams of
visualize
making
normality in R. You can
that.
understand how normality works in
Even
R.
Ramsar, I
And
used to tell,
Shapiro
we
test
have
is
one
a
medical
more direct,
equipment
simpler,
team here.
robust way to understand
He
if
was
your
like, no, we
if
don't
your
deal with
variable is
medical equipments
normally
and all.
distributed
We
or not,
study
right?
humans, we
So
analyze them,
it
and we
has
put them into
normality to a
more
certain extent,
meditation,
but it is
put
again
them into more of
when I do the Shapiro
silent
with normality
music,
test, it does
then
not
yoga,
hold that to
all
be true,
of
right?
this
And if
without
I
any
repeat the same
medicines, we
test,
try to
Shapiro
pull them
will
out of
for
this.
my second
And
variable,
even after doing that, we
which
can't
is
carry
the
it.
outcome variable,
And
the Y,
one yoga session
I
will be
can
around
see
3,000,
that is
4,000.
again
This is how he
not
was
normal, right?
explaining to us.
So also there are
See, the thing
different
is, for
views
any
when it
change
comes
to
to
happen,
normality,
first the
and if
person
it's
want to
not met,
change.
what do we
That's the
do,
first thing
right?
that has to
You
happen.
would know that
So
when
that's first
normality
is
is
drug
not met,
problem or whatever
we
is drug
usually
problem
go
that has
for
to be
non
controlled through rehab. After
parametric
that, it
tests,
will come
right?
back with
For
senses, and then you
non
can correct the remaining like trauma related stuff and all what has
normal
happened to him
data.
and stuff. And by the end of the day, you want everybody to
And
survive. That is the concept
parametric
of
tests
therapy. Like you want to,
are
if not a
usually
big progress, they should
for
be able to survive
normally
and just live
distributed
through
data,
their life.
right?
So first the drug problem,
But there are
whatever it is,
different
that has to be
cases, as you would
resolved.
see from the
First like it has
literature,
to come down.
where
He is
folks have used
international.
linear regression,
His
even
mind
if
is
the
full.
case for
He
normality
works
has
with
not
medical
met.
fields.
And there are
In
different reasons for
medical
it,
shops and all.
and
He
there
has
are
a
different
certificates
solutions
and
to
all.
it as well.
From
Some
there,
people go
he
with
tell us
ordinary
whatever he
least
gives,
squares
we don't
method,
consume.
which are more
Where we
robust when
drug
it
off, we
comes
are
to
also
non-parametric
From
assumptions and
past
the
7
tests,
years,
which
he's
we'll
with us. We
cover in the
always
advanced
try to
stuff.
change
So
it,
don't
but
worry
he's
about
not
that right
changing.
now.
If we
So
try to
right now you
change
just
it,
need to
he
know
gets
that both the
irritated
variables are
and
not
he'll
normally
run.
distributed.
And he'll go
But
to bar,
you need
drink.
to know that
He'll
this is
tell, I'll
one
stab
issue
you
when
this
it comes
tonight, I'll
with
kill you
that comes with
everyone and kill you.
large data sets,
That
right?
day we'll
So as
deactivate
you can
this
see, this
bar owner,
has
he'll sleep
around
outside.
5,000 participants. And
So
when I
that
say
is the
large
issue.
data set, I mean usually the
His
traditional
screwdriver is
psychology
from
data sets that usually have data from, let's say, 300 to
So
500 to
actually, I'm not sure
800 or
about this
1,000
fan.
participants in
That
my
fan
knowledge, right?
has a lot of power.
And I rarely have
So
seen
in case still you feel
lab studies
when you're
or
using
simple
one, two,
surveys that
three,
have
you
more
feel
than
same thing, then I'll call the
2,000
countdown.
data points. Of course, that
We have
usually happens
witnessed
when you have large scale data sets, when you have large scale studies being conducted
that will share, sir.
multinationally
It's
and stuff
not
like that.
burned or something.
But
It's
usually this
around
happens
4
with
5
large
years
data
something.
sets that normality is usually affected by the huge data set that you have. And this issue we will cover in much more detailed manner in later sessions, in more advanced sessions. Right now, you just need to know that these two variables are not normally distributed. But again, we're just going to go with linear regression anyhow to understand the linear relationship between these two variables. And also the aim of this session was to just understand how regression works, right? So we're going to go ahead with that. Now, third thing that we need to know is before running your linear regression syntax in R or tests in R, it is very important to do correlation test first, right? So correlation test is most of the times a precursor to your regression. So there are different ways, a couple of ways in which I do this in R. One way is just writing cor, which represents correlation, and R is going to show you that there is a function that exists by this name cor. Then I open it, and then I mention my x variable, which is contained in this data set. Sorry, yeah, SMU hours, and then I mention my y variable, which is again in the same data set, academic scores, right? And I can also mention whatever method I want. So there are three kinds of tests that you can do, three kinds of correlation tests that you can do. You can do either Pearson, you can do Spearman, you can do Kendall. So all three of them have different assumptions, of course, as you would know based from our previous sessions on correlation. So right now I'm just gonna go with simple Pearson test here. So the default is Pearson. Even if I don't mention anything, it's gonna take Pearson's as default. And if I run this, can you see this? there's a very strong negative correlation between our two variables, right? So it essentially tells us that if the value of x increases, the value of y decreases. Or in simpler words, if the social media usage hours, number of hours that people spend on social media increase, their academic scores decrease, right? And this strong correlation means that this relationship is quite strong between these two variables. Also, just one warning here, one disclaimer. This is a simulated generated data set that I created before this session, and this may not be accurate at all to derive inferences for real life phenomena. So this is just strictly for learning purposes, right? Now, now we're gonna jump on how do we do this in R, right? Now the main thing comes, the main hero of our heroine of our story, right? So how you would do this in R is you would just name your variable as, let's say, any random variable. Let's say I would like to store my uh, uh, regression test in reg model. This is just random variable name that I've created. And the syntax is you would use this function lm, which stands for linear modeling, right? Linear model, right? So you would use this function lm. Then if you would open the bracket, it's gonna give you this hint that first you have to mention the formula, then data, and stuff like that, right? So the formula would be the dependent variable on the left hand side and the independent variable on the right hand side, right? So in our case, the dependent variable is SMU hours, and then I would use this sign which is called, which is usually used in this in a formula. I think this is called a tilde, if I'm not wrong. I'll just get back to you on this. I'm not sure, but this symbol is used to show that I would like to understand the effect of the variables on the right, which are my predictors or my explanatory variables or my independent variables, on the dependent variable of SMU hours. Yes, I see a question. Yeah, yeah, Vasundhara, please go ahead.
Hi, could you let me know? Yeah,
Yeah, can you hear me?
Yes, I can hear you.
Yeah, so I was saying that.
Hello, am I
Yes.
audible?
Yes, Vasundhara, yes.
Yeah, so I was just saying that this sign that you just inserted, where could we find it?
It's on your keyboard, just below escape key or
Okay,
above
yeah, I
tab.
saw it.
Got it?
Yeah, thank you.
Yeah, no worries. 1 second. Let me just confirm for all of you what is it called. Okay, I'll just get back to you later. Sorry. I hope I have not muted myself. Okay, cool. Okay, getting back to this. So we use this symbol to demarcate our formula. So I'm just going to finish my formula by stating the ID, which is academic hours, right? So this is the formula, right? So you need to know that your linear regression works on a particular formula where you specify your y, which is your outcome variable, and your dependent variable on the left hand side, and then followed by this symbol, and then your independent variable, which is your which is your sorry, I did this the reverse, so that is my fault. So my dependent variable is academic hours, which I have measured, and the one that I'm trying to see the effect of is my social media hours, right? So this is my dependent variable and this is my independent variable, right? And you can't switch them, right? So your independent variable cannot come here and your dependent variable cannot come here. This has to be followed like this. So essentially what you're saying is you're trying to study how academic scores or academic, academic scores change with changing social media usage hours, right? And then once you mention this formula, then you put a comma and then you write your data set, right? So you just mention what data set you want R to use. So these two variables are contained in this data set, which is R data 1, right? So I'm just gonna run this. So R tells me there is an error. So maybe I've misspelled something. So academic score was 1. Yeah. Now I think it should work. Academic scores. Cool. Right. So R has stored this linear model, where we are essentially studying the effect of social media usage hours on academic score, or in other words, we are saying we are regressing academic scores against social media usage hours, or in more simpler words, we are saying that we are trying to see how academic scores change as social media usage hours change, right? So this is what is meant by this whole equation syntax. Now we have stored this in this variable which is called reg model, and you can come with any other name. It can be rm, it can be m1, it can be any random variable name that makes sense to you. So do what you feel like right there. Now, just to see the results, we can just do summary of our regression model, right? So till now, what we have done is we have stored regression model in a particular variable, our linear model in a particular variable, and now we just want to see, the results, right? So for that, we'll have to use this command summary and then mention the model which we want to summarize. Now R gives you a bunch of things, right? And this is where the fun starts, right? So the main question is how to interpret the results. What does intercept tell us? What do these estimates, different estimates tell us? How do we make sense of R square values and all of that? So we're going to focus on it right now in this session. Till now, any doubts before we jump to how do we interpret results in R? Or just interpret the results of linear regression. Any doubts till now? Okay, let's just continue. Got it. Cool. So firstly, I'm going in a very chronological manner. So when you call for the summary of your linear regression model, R gives you different bunch of values, right? It gives you minimum, it gives you first quartile, median, third quartile, then maximum. This is just your descriptive stats. You can just ignore it right now. This is the important result that R gives you, right? This is the important result to consider. Now, it tells you that your intercept is 84.91, right? And your estimate for social media usage hours is minus 3.6, right? So I'm just gonna go back to our plot, right? So as you can see in this plot, this line, whatever I've drawn, the blue line, just focus on the blue line, right? This would have a certain slope and this would have a certain intercept. Intercept is the distance covered by a particular line on the y-axis. So here the intercept would be, as you can see, it's a little above 80, the mark 80. So it tells you that the value covered by the line when x equals to 0, right, at this point. So this would be somewhere around 84, as you can see. So R tells us that it's near around 85, so 84.9. And then the estimate for SMU hours is minus 3.68. So so what it essentially means, the minus sign means that as your social media usage increases, the number of hours increases, your academic scores decrease by minus 3.68. So let's say if there is 1 hour increase in the social media usage for a person, their academic scores are predicted to decrease by 3, right? So this is what we do here, and this is what we mean here. And then your p-values are stated here in the last column, and as you can see, this is highly significant result, this one. So this tells us the effect of the main effect of social media usage hours on the outcome variable, which was academic score, right? So this is what intercept and estimates tell us. Now moving on to R square values, right? As you can see, there are 2 R square values that are reported here. One is multiple R squared and second is adjusted R squared. Usually both of these values are different, but since our data is simulated and it strongly hints towards one side of our hypothesis, that's why both of these are quite similar. But we usually go for adjusted R square, and the reason for this is quite simple. that usually in real life, data sets or in research questions that we face, we rarely study linear relationship. We usually try to study the effect of two or more relationships on one outcome variable, and in that case, to adjust for a lot of variance that comes in with different kinds of independent variables, R gives you this reliable value which is called adjusted R square, and that's what we go for, right? And just for now, just take it as a thumb of rule to report your adjusted R square, which is more important than your multiple R square, and to report your estimates and p values. These three are quite important, right? So now, bringing it all together, what does it mean, right? So the resulting regression equation can be written as this. So if you would remember, at the beginning of this tutorial, this presentation, I talked about this linear regression, right? Where y equals to beta naught plus beta into x plus e. Now I'm just gonna go over it and contextualize it in terms of an example, right? So y is the outcome variable or the dependent variable, right? Or in our case, it is the academic score, right? And beta naught is the value of y when x equals to 0. Simply, if you put x equals to 0 in this equation, so if I put 0 here, so this whole term becomes 0 and then y becomes equal to beta naught. Now, one thing that I have not explained here is e, right? You must be asking what is this e, right? In a lot of textbooks and in a lot of tutorials, you may see just the whole linear regression like this to simply make you understand what linear regression is. But I usually include the e because e represents the residual errors, right? So as you can see, this is the line, right? The blue line. Can you see the line on the plot? The blue line, and different data points are are at a distance from this line, right? For example, the one just above the line is at a smaller distance from this goodness of fit line as compared to the one on the extreme, right? So the residual is the distance between the main regression line and the data point, right? And it just tells you roughly that how much variance is there in your data set and how much variance is there in your data set. And right now you just don't need to focus a lot on it. Just understand that E represents the error in variance that you have in your data, right? And this is usually very small in most of the data sets. So that's why some people usually ignore it and just write this much to represent a linear regression equation, right? So coming back to our regression equation, so beta naught is the value of y when x equals to 0, right? Very intuitive. Until now, I think everyone understood this. And beta is the coefficient with value of x variable, right? So in our case, beta would be minus 3.687853 or simply minus 3.68. And x is the value of your independent variable value. So our equation would become y equals to 84.913, which is the estimate when x equals to 0, plus minus 3.68 into value of x, right? So simply stating, we are saying that academic scores are equal to 84 minus, minus 3 into number of hours. So let's say, let's try to test this out. Now, what will be the score for someone? What will be the academic score for someone who spends 10 hours on social media in a day, right? So when we have our equation ready, we can calculate this simply by saying that their academic score would be equal to 84.913298 minus 3.687853 into 10, right? So this will tell me how much their academic scores would be. So when I run this, R gives me that the predicted academic score for this person would be 48.03, right? So this is how we do, this is how you can predict based on your data, your tests, and your relationship. Since we have established a strong cause-effect relationship, a strong linear relationship between these two variables, we can confidently say that when someone spends a lot of hours on social media on a daily basis, their academic scores significantly goes down, right? Now, is there any problem or any question in this example? before we jump to our second example for the day and then end the presentation. Any questions till now? Yes, Bhumika, please.
Yeah, so I think I lost the track where you were trying to draw a relation between the beta naught and its part in the equation. So I couldn't understand that part.
Right. So beta naught is essentially the value of y, which is your outcome variable, dependent variable, in our case, academic score, when your x is 0, right? So let's say for case where someone spends 0 number of hours, on social media, in that case, what will be the y, right? So it's simply your estimate of your intercept, which is 84.913. Is that clear?
Okay, yeah, it's clear.
Cool.
Thank you.
Sure. So let's jump on to another example to make this more clear. And also, guys, after this presentation, I'm going to send the second data set, which is salary data. And you guys can practice on your own. And please feel free to ask any questions on the group, or if you have it right now too, that's not a problem, right? So the second data set comes from Karthik Veerakumar from Kaggle. He uploaded this there. And this is just salary data. So I'll just show you what this data has. So this data has salary as per the number of years of experience that someone has, right? So if someone has 1.1 years of experience, they have salary of, let's say, 39,343 rupees per month, something like that, right? And this has 30 data points. Now it's a very fairly simple data set. Then we can jump directly to plot. So here we are trying to understand how numbers of years of experience affect the salary of an individual, right? So fairly simple to study. So first we can just plot. And as you can see already, I mean, as a researcher, you can see from this visualization that as the number of years increase in this plot, the salary also increases, right? I mean, they both are kind of related, as you can see. So the point here, where someone has around 11 or 12 years of experience, their salary is also quite high as compared to others, right? And vice versa. So if someone has less number of years of experience, the salary is also low, somewhere around 40,000, 30,000, right? And then just to add a regression line, I can just do this here. It gives me this error that I have an extra bracket. Yeah. As you can see, there's a very strong linear relationship between these two variables, and this line tells you that. Now, what I can do is I can just do correlation to understand the exact relationship in terms of numbers, in terms of a quantified number between these two variables. So what I can do is just mention my data first, salary data, and mention my x variable, which is years of experience, and then I can try to see its correlation with my y variable, which is my salary, right? So, so it again gives me this very strong positive, relationship between these two variables. What it essentially simply tells us, is that when the numbers of years of experience increase, the salary of the person increases. And your plot shows you that, right? You can see a very strong positive linear relationship because it increases. The line is heading towards a positive value, as compared to this plot where it was decreasing as x was increasing, right? Here, the y increases with x, and in this case, y decreases with x. So it also gives you a rough estimate of whether the relationship is positive or negative, right? The plotting and visualization. Now we can directly jump to a regression where we mention our salary as the outcome or the dependent variable on the numbers of years of experience. So the syntax is fairly simple. We start with a linear regression. I'll just rewrite this for you. Syntax is linear regression. Then we want to understand how salary is affected by our variable, which is years of experience. Years experience, and the data set we are using this for is salary data, right? So this is stored in this variable called rec mortal1, and now just to see our results, we can run summary, right? Again, so it R tells you that the relationship is significantly, significant to a very high extent, where it's much less than 0.001, and it tells you that a person with no salary, no years of experience, 0 years of experience, has a salary of 25,792, which is our beta norm, right? Again, iterating to a point, to our point, previous point, where we say that beta naught is the value of the outcome variable, which is our salary, when x is 0. So if someone has 0 years experience, our tests tell us that they have a salary of 25,792 rupees per month, and as their experience increases by 1 unit, which in our case is 1 year, their salary increases by 9,450 rupees, right? So our tests also tell us this, and also adjusted R square is quite strong. It is 0.9554. Also, again, one thing that I forgot to mention before was your R square values range from 0 to 1, so it never goes above 1. And you can multiply this adjusted R square value with 100 to understand the percent of variance that your independent variable explains in your dependent variable. So what essentially tells me that 95.5% of the variance in my outcome variable, the y variable, which is salary, is explained by the number of years of experience, right? That is the independent variable. Now, putting this all in our equation, where we said that y equals to beta naught plus beta into x, we can say that y equals to 25,792.2 plus 9450 into x. So, or in other words, salary would be 25,000 this plus 9,450 into number of years of experience. Now, let's say if we want to know the salary of someone who has 20 years of experience, right? Right. So we can simply do this in R by putting this formula. I mean, just manually doing this, just checking and predicting their salary based on our data set. 9450 into 20, right? So this is our equation. So their salary per month would be 214,000, which is around 2,14,000 per month, right? So, usually we don't do this manually, of course, but then it's always a fun way to play around with your data, to play around with your results. And once you've established a strong linear relationship between two variables, you can see that it gives you this power of estimation, this power of prediction based on your given insights, right? So just to reiterate, linear regression is a very powerful way of and very simpler way of representing the cause-effect relationship between two variables. And it also helps us understand the predictive effect of more than one variable on a particular dependent variable. And essentially, we explore the linear relationship between two variables, right? So that's why we do linear regression. More advanced version of a linear regression will contain multiple, independent variables, where we have y depending on x1, x2, x3, and so on, right? So those are the more advanced version. But today, since we were just covering the basics, hence we just looked at one-to-one relationship, where we just had one of the x variables, which is independent variable, right? So yeah, I hope it's clear. And um, unless you do this in R yourself, it's gonna be difficult to understand, how to navigate R and understanding this, to understand and to do this actually. So I would urge everyone to do this in R. If you have any questions, feel free to reach out to me, Munna or Pooja, or feel free to ask this on the group. And if you need any resources in order to help you understand, we are always there. Yeah. Now, any questions related to this session or any particular example that we used or any theoretical question that you may have, please ask. Okay. Okay, so I don't see any questions. Don't worry, just go back and try this in R, and I'm sure you'll find it quite fascinating. Some of the stuff, and some of the stuff you may find it challenging as well, depending on your point wherever you are in learning R and your art journey. So if you have any questions, please, I would urge you to reach out to us. Do not hesitate from asking. We are a club that has a lot of folks who have just begun in art, so do not hesitate to ask your questions. Okay, and I'm gonna send yeah, Vasundhara, do you have a question?
Yeah, Ritik, you just wrote y is hashtag y is equal to x1 plus x2. Could you just let me know what does that mean?
Yeah, so I was just trying to explain how in these two examples we have just looked at the effect of one variable on the outcome variable, right? So in our first example, we were just trying to study how social media usage, the number of hours that you spend on social media every day, how that affects your academic scores, right? And in the second example, we were looking at how your numbers of experience affect your salary, right? So you're just trying to do this one-to-one relationship. But in future, you may have multiple independent variables and only one dependent variable. For example, in my previous example, the first example that I explained, if you're trying to understand the effects of stress, eating patterns on mood scores, right? So there might be more than two or three, variables that you have measured as your independent variable, and you're trying to study their effect on one dependent variable, which is mood score, right? That's why I've just written that this equation can go on and on and on, where x1, x2, x3 are all additive, and they will have additive effect on your y variable, which is the outcome. Is that clear?
Yeah, thank you so much.
Okay, no worries. Cool. Um, yes, Ikra. Where can I learn R as a beginner? Can you suggest me some resources? Yes. So, frankly, you are at the right, and you are in the right club, right position. So don't worry about that. Just stay tuned and stay regular for these tutorials. And I would really urge you to go back and try doing R yourself, and you would find a lot of helpful stuff on our pinned messages on our channel. So feel free to check them out. And we also have a whole resource list on R, on different aspects to it, divided by different levels. If you're a beginner, if you're an intermediate person, or if you have an advanced learning understanding of R, there are different resources available to you, to check out. So feel free to do that. Plus, we also have a YouTube channel where we have just uploaded our past recordings. So if you have missed out on those lectures or those tutorials, feel free to go back to them and watch them. Okay. Munna can give you the link, or if I am there, I'll give you the link to that. Don't worry for that. All right.
Okay, thank you so much for that.
Okay, no worries. Okay, then everyone, thank you so much for joining us. I hope all of you learned some bit of linear regression from this session. And please go back and use the datasets, or you can have your own dataset and repeat the same analysis in R. And if you face any issues, feel free to reach out to me or Munna or Pooja or Macarena or Tanushka, right? Or just post it on the channel as well. We'll get back to you. Okay. Thank you, everyone. Good night, good evening, good afternoon. Have a nice day, depending on wherever you have joined us from. Thank you, everyone. Bye.
Thank you.
Thank you.